All right, folks, so here is a lesson on related rates. This is probably going to be at least two-part lesson, but we'll get the majority of it done right now. Okay, so the first thing to note is that this particular question does not have context. Okay, so it's going to be a little bit weird at first, but this is just to lay the foundation. So let's say you have something like to the left right here. Okay. All right. Now, historically speaking, when you take the derivative of this, it becomes that. And when you take the derivative of this, it becomes this. And we add a y prime. That's not y to the that is not y to the power of 1. That's not y. That's a y prime. We add a y prime over here because of the chain rule. And one way to interpret that is that this is your independent variable. This is your dependent variable. Okay, so you add a y prime and you use the chain rule on whatever your dependent variable is. Okay, that's one way to conceptualize it. So now, however, now y and x are both going to be dependent variables because now there's a third variable in terms of t. Okay, so y and x can be expressed in terms of t. So y and x are dependent upon t. Therefore, y and x are both going to be subject to the chain rule later on when you take the derivative. Okay, the way I like to conceptualize it is similar to what parametric equations are. You can think of y as a function of t. This is a function I completely made up. Same thing with x. X is a function of t. Here's a function that I completely made up. Okay, so yeah. Okay, so what we're going to do is we're going to take the derivative of both sides. So we're going to get, instead of dy over dx, this is going to be, okay, dy over dt. And then you take, let's look right here. This is your original function. Okay, you're going to get dy over dt right here. Okay, let me actually say it this way, step by step. When you take the derivative of invisible 1 times a variable, you just get 1. Okay, now y is going to become y prime, or you also got to add a y prime, I should say, okay, because of the chain rule. And instead of y prime, I'm just going to say dy over dt. Remember, in this context now, both functions you can think of parametric equations are in relation to t. T is your independent variable. Both y and x are your dependent variables. So y and x are both dependent upon t. So that's why it's dy over dt, not dy over dx. Okay, so again, 1 times a variable, the derivative is 1, but because y is dependent upon t, we got to write y prime, which in this case is dy over dt, not dy over dx. And then you take the derivative of x right here, and you get this, okay? And then, however, we got to use chain rule because the inside is not a clean x, okay? So we do the derivative inside here, which is negative 2x. And don't forget, x is also subject to chain rule because it's dependent upon t, so I added dx over dt in the end. So we should understand the greens here, ignore the blacks, okay? Now, the 2's cancel, all right? You're left with negative x, okay? Negative x on top, all right? So that's how I got this negative x, and you're left with the 25 minus x squared inside the root right here on bottom, okay? So we should understand how these 3 green highlights became that, and then your dx over dt is right here. And now we just simply plug in, folks. We plug in 3 feet per second for dx over dt because that's what's given, okay? We also plug in 4 for x, okay? So I want you to see how I plugged in over here at all those green highlights, okay? And then 25 minus 4 squared, which is 16, is square root of 9, which is 3. Negative 4 over 3, the 3's cancel here, and you're left with negative 4. Okay, that's example 1. Let's look at example 2 right here. Now, basically, we're given a volume of a cone, okay? And we are going to rewrite our, and it's also given that if you look at all these highlights here, okay, yellow highlight, yellow highlight, yellow highlight, Okay, height is 3 times the radius, so h equals to 3r. We can isolate r and get r equals to 1/3 h. Okay, so we're going to substitute in 1/3 h for r right here. Okay, right there. So now we get this, okay, we get this formula over here. This is v, not r, by the way. Okay, this is v. Now we get this formula over here after we substitute in r. So the reason we substitute it is 2 reasons. Number one, we want to minimize the amount of variables. So right now at the first step, we have 3 variables. We want to minimize the amount of variables. So we substitute in, we either want to write this as all r's or all h's. Okay, so in this case, we're writing it as all h's. And the reason we're writing it as all h's is because in the end at some point, you want to find dh over dt. So we want to rewrite this as all h's. So at some point, we use a chain rule and you get a dh over dt over here. If we rewrote it in terms of all in terms of all r's, then you get a dr over dt here, and it's not asking for that. Okay. So again, we rewrite it into all h's, so at some point it can produce through the chain rule a dh over dt, which is what we want. Okay, so now it's just algebra over here. 1/3 squared. 1/3 squared is 1/9 times 1/3 is 1/27. Okay, pi gets carried downwards. 2 h's here, 1 h here. There's 3 h's total. When you multiply with exponents, remember you add. And now you take the derivative because this is the most simplified form. And then pi over 27 is a constant times the variable, so the constant gets carried down. This becomes 3h squared. And remember, it's all in, both h and v are in a relation to t, so they are dependent variables. So there's going to be a chain rule for h here, okay? And there's going to be a chain rule for v here. This is 1 times a variable. You take the derivative, it's 1. And then remember, chain rule means it's v prime, which is the same as dv over dt. Okay? All right, and that is the second example. Third example is right over here, folks. Okay? So let's get rid of some highlights over here. Okay? So basically, this diagram, okay, you can take your own time to read what's going on over here, press pause. This diagram right here is a representation, okay, of what's going on over here. Okay? We have 15-foot ladder, okay, leaning against the house, which is here, okay, and then we have it's 5 feet. Oh, and this is the base of the ladder. That's the base of the house, and the distance is 5 feet right here. Okay, okay. So again, these 2 pieces gets used right here. And this is y. I'm going to call that height y. Now, the thing with related rates is that you can, with these related rates problems, you can use any kind of formula. But usually the most obvious one will be the simplest route. Okay? And the most obvious formula to use when I see a right triangle, okay, this is a right angle, is going to be Pythagorean theorem. So I'm going to do x squared plus y squared is z squared. Okay? So we get 5 substitute in there, all right? Y stays the same because we don't know y yet. 15 gets substituted in for z, okay? And then I isolate y and I get 10√2, okay, when you just do the algebra. So I got 3 values now. I got 5, 15, which is given, and then I also have the 10√2 here, okay? Now, here's where the magic happens. I get x squared plus y squared equals to z squared. Okay? Now, I'm going to plug in the 15, okay? I'm going to plug in the 15 over to z squared. Okay? I'll plug in the 15 into z squared and get this. Okay? Now, I'm going to take the derivative of this and the derivative of this and the derivative of that. Okay? So these 2 derivatives become that. And then because of the chain rule, because these are both dependent upon t, I get dx and dy over dt. And the derivative of any constant is just 0. Okay? And now I just plug in. Okay, for x, all right, for x, I got 5, which is given. Okay? for dx, okay, for dx right here, I get 2, which is given, okay. For y, I solve that right over here, okay. dy is what we want, okay. So I leave that alone, dy over dt, I mean. And then you basically just do algebra. 2 times 5 times 2 is 20. Okay, move that over, you get negative 20. You minus 20 from both sides, I mean. And you divide it by, this is 2 times 10, which is 20 root 2. So negative 20 over 20 root 2. These 20s cancel, you're left with a negative 1 on top over root 2 feet per second. Okay? Now, some people may say, well, Mr. Chen, how come we only plugged in the 15 here? How can we plug in the 15 over here? And how come we didn't plug in the x and the y over here? Well, if you plugged in the x and the y over here, okay, well, let me just put it this way. If you plugged in let's say we plugged in the x over here. Sorry, let's say you plugged in the x over here. So that was 2. Sorry, I just blanked out right there for a second. Let's say you plug in the x right here, which is 5. Okay? So you're going to get a 5 squared. Okay? You're going to get 5 squared, which is 25. Okay? Which is 25, and then 220. And then so basically you get 25 over here when you plug in. And when you take the derivative, you're going to get 0 and 0 here, because a derivative of a constant and a derivative of constant is going to be 0. And so this is basically not even going to exist. Okay? And you're going to get 0 divided by this 2. You're going to get, basically, remember, this is not going to exist. You're going to get 0 divided by this right here, which is going to be 0 divided by this is going to be just 0. So this is going to go away. And so you're going to get dy over dt equals 0, which is, it's going to lead us to a brick wall. Okay? Now, let's see what happens if you plug in, and something similar happens. If you plug in y over here for 10 root 2, you're just going to get, when you take the derivative of this and plug in 10 root 2 squared, and you take the derivative of that, you're going to get a 0 here. That's going to eliminate that, and you're going to get a 0 times dy over dt, which becomes 0. So the dy dt is going to go away. Okay? So that's why you plug in, you leave the x and the y. Okay, and another way of thinking about it is that your 15 doesn't change. The length of your ladder doesn't change. Okay, it's fixed. Okay, but your x and y do change, because as the base of this ladder slides to the right, this 5 increases, and as the ladder slides to the right, that means this decreases. The top of the ladder slides downward upon the wall of the house, so this y decreases also. So x and y are dynamic variables, they change, so that's why we don't substitute that in. Okay, that's probably the better way of thinking about it. X and y are not fixed, okay, they're going to change. All right, so you plug in the number that is fixed, which is the 15. Okay, that wraps up the lesson. Thank you for tuning in, folks.